Welcome, ladies and gentlemen. This is a video on theoretical yield, calculating both theoretical yield and percent yield, and talking about types of problems with this and essentially knowing what to do. Now, I'm hoping that that more of you will watch this particular video because I know I'm not doing an example of this in class. So here's where watch this. If you have questions, come on in. We can talk about this. Theoretical yield and percent yield. Theoretical yield is essentially exactly what the name says. It's how much product you are theoretically supposed to get when you do a reaction with a certain amount of reactants. It's based off of the limiting reactant. So limiting reactant problems, you're identifying which reactant runs out first, typically. Theoretical yield is saying how much product you get if compound A is your limiting reactant. How much should you theoretically be able to produce based on the amounts you have, based on which reactant you know is limiting. Now, in order to calculate theoretical yield, it'll depend greatly on the type of problem that you have. If the problem identifies the limiting reactant and says, yes, compound A, that is the limiting reactant, then in order to find the theoretical yield, all you have to do is a mass-mass stoichiometry problem. The answer to that mass-mass problem will be your theoretical yield, because what you're doing is saying, all right, if I know that compound A is the limiting reactant, then I can figure out theoretically how much product I should get through simple mass to moles, moles to moles, moles back to mass. That's what I mean when I say mass-mass. But if the problem does not identify the limiting reactant and instead says you start with 10 grams of compound A and 20 grams of compound B, what's the theoretical yield? Then that becomes a limiting reactant problem where you need to take each of those masses, and we talked about that, how you know it's a limiting reactant problem. If the problem gives you information on two reactants, you've got to figure out which one will run out first. The theoretical yield will be how much basically the lesser amount of product, whichever reactant, the amount of product you get from the limiting reactant. Percent yield, on the other hand, is simply a comparison between how much product you actually obtain versus how much you theoretically should have gotten. Percent yield is calculated essentially like any sort of grade that you've ever gotten in any class ever. Theoretically, you should know the answers to all of the questions on all of the tests all of the time. Theoretically. Have you? No, I highly doubt that you haven't actually gotten all test questions in your life correct. So your actual yield is how many you actually got right. Your theoretical yields, you should have gotten them all right. The comparison of the two is percent. Is the percent. Did you get 95% of them right? Did you get 90% of them right? It's the same thing in chemistry. Actual yield compared to theoretical yield. Now, the sample problem that I'm going to do here is one that identifies the limiting reactant. As you can see, we've got a chemical reaction supplied, and it says when 150 grams of iron 3 oxide, that's how we would name that compound, are used in the above reaction as the limiting reactant, so it is identifying the Fe2O3 as the limiting reactant. What is the percent yield if the actual yield of Fe solid was 87.9 grams? And before I go into this, I'll just talk about the distinction. What if they didn't tell us that Fe2O3 was limiting? What we're going to do here in order to solve this is one mass-mass problem. We're going to take the mass of the Fe2O3, the 150 grams, and we're going to figure out how much product we should theoretically be getting. If the problem did not tell us that the Fe2O3 was limiting, we would simply be doing two mass-mass problems. That's the only difference. We would do the mass-mass problem twice. We would basically take each of the masses for the two reactants and figure out which one is going to give us less product. That is the only distinction there, whether you're doing one mass-mass or two mass-mass, but it's still a mass-mass question. So, back to this particular problem. It's asking us to calculate the percent yield. So, what do we need? Percent yield. Percent yield is actual divided by theoretical times 100. When we look and we read through this particular problem, pulling out the information, it says that we have 150 grams of the Fe2O3, and then it says right here, the actual yield of Fe solid was 87.9 grams. That means that we already know this top number. This top number right here is 87.9 grams. The problem gives you the actual yield. That's actually fairly common in percent yield problems. It's fairly common for them to supply you the actual yield and then ask about percent. So that means in order to solve for the percent yield, we have to determine theoretical. And the way that we calculate the theoretical yield is through a mass problem. We need to figure out how many grams of Fe, and we know it's Fe because it says Fe here, so we want to use the same product. We're not interested in the carbon dioxide. We're talking about the Fe solid. How many grams should I theoretically get from this 150 grams of the Fe2O3? So that's what we're going to do. We're going to figure out how many grams of solid iron we should have gotten based on that 150 grams of the iron 3 oxide. And that's mass. So this is a dimensional analysis problem. I'm going to start with 150 grams of the Fe2O3. Gut check reaction, AP chemistry, you see grams, you're going to turn it into moles using gram formula mass. So 159.6 grams Fe2O3, that's the gram formula mass. That's the mass of 1 mole of Fe2O3. That's just GFM, right? 2 ions, 3 oxygens. So that gets us to moles of Fe2O3. Now we're going to use the coefficients. Now we're going to say that for every 1 mole of Fe2O3, it should be producing 2 moles of iron solid. So this is our coefficients. 1 mole Fe2O3 makes 2 moles of Fe. Moles of Fe2O3 have canceled. We do need to take it one step further. You do need to convert it into the mass. You can't leave it as moles of iron. And the reason that we have to in this case is because we have grams of iron here. Now, if you wanted to simply go to moles and stop, that could work too, but you'd have to convert the grams, the 87.9 grams, that actual yield, into moles of iron, and then still do the comparison that way. I think it's a little bit easier. You're doing the same work either way. I think it's a little bit easier to keep going with this particular dimensional analysis and turn the moles of iron back into grams of iron. So we're using the GFM of iron. 1 mole of iron has a mass of 55.8 grams. Moles of iron have canceled. We now have grams of Fe. We go through, we do that math. Straightforward, multiply everything on the top together, everything on the bottom together, divide the top by the bottom. We get 104.9 grams of Fe. This number right here, this is your theoretical yield. That is saying that when we start with 150 grams of the iron 3 oxide, we should be getting 104.9 grams of iron solid. Theoretically, if everything goes perfectly, but as you can see, it didn't go perfectly, so now we're going to bring it back to the percent yield. Actual, they told us that in the problem, 87.9 grams. We only actually got 87.9 grams. Theoretically, which we just figured out, we should have gotten 104.9 grams. So this number is becoming the bottom. That's our theoretical yield. And then just multiplying by 100 when we're done. When we do this work out, taking it to 4 significant figures, 3, based on the 87.9, 3 sig figs, I get a value of 83.8%. 83.8% for the percent yield. So the theoretical yield was 104.9, which we had to calculate. The actual yield was 87.9. It was supplied in the problem. Compare the two. Actual divided by theoretical times 100, that's your percent yield.